Okay. What questions may you have or do you have? Anyone? Okay, well, then we'll just go over some practice problems from the back of the book. These are problems that don't have answers in the back of the book, but we'll give them a try. This one is from stoichiometry. And we'll just get going, okay? If you're okay with that, give me a thumbs up. Okay, so I'll let you read this problem here. Can you see the screen, the problem in front of you? Is that good? Okay. So here's a reaction. What mass of methanol, oh, that's an incomplete sentence, right? What mass of methanol can be produced if this reaction has a 74% yield under certain conditions? I'm missing a good part of this problem. Let me find this problem in the book. What number is this? Here it is. It should be what mass of methanol is required to produce 1.0 liter of methanol if this reaction has a 74% yield under certain conditions. Okay, so the reason I like this problem is it tells you what 74% means. So 74% is equal to 74 grams of methanol obtained per 100 grams of methanol theoretical. Okay? So they want to know what mass of methanol do we need to produce 1 liter, and they don't mean 1 liter theoretical, they mean 1 liter actual. Okay, so you can see that the end result is how many grams of methanol do you need? That's the answer. If we start off with 1 liter of methanol actual. So here's where we're going to begin, and here's where we want to end. So do you follow me so far? We good? Now we need to kind of fill in the blanks here. So if we get 1 liter actual, I think we can calculate the grams actual, but here, since we have the density as grams per milliliter, maybe we convert this into milliliters actual and then into grams actual. Okay? And I see I need more room to work here, so I'm going to kind of go down here. If I have the grams of methanol that I actually want to get, I can calculate the theoretical because of this up here. And if I have the theoretical amount of methanol, then, well, shoot, that's it. Sorry. Okay, so I'm going to write this pathway out again. We're going to start off with 1.0, and I think that's only 2 zig figs here. So 1.0 liter of methanol is what we want for our actual amount that we get. We're going to turn that into milliliters of the actual that we're going to get. And we'll turn that into the grams of the actual that we're going to get. And since the actual differs from theoretical, we'll turn that into the theoretical grams of methanol that we need to make. And I believe that's what they're asking. What mass can be produced, or what mass would produce 1 liter? So this question here, and I'm going to write this again, what mass of methanol would produce 1.0 liter of methanol? What they're really asking for is what mass theoretical would produce 1 liter actual. So I'm not sure if you get the nuance of the question, but that's kind of it right there. Okay, so it's a little tricky the way it's worded. So nonetheless, if we follow this, we have 1.0 liters of methanol. Now this is what I'm going to write for methanol. It's a common chemical abbreviation for methanol, and biology uses it too. Times 1,000 milliliters of methanol to 1 liter of methanol. And then the density we see is 0.791 grams per milliliter. So I'm going to put 0.791 grams of methanol per 1 milliliter of methanol. And what I should be doing here is I should be putting, this is actual, but I didn't do that. So I'm going to put, we're going to get, what is the percent yield? 74 grams of methanol per 100 grams theoretical. Okay. So you can see that this number that we're going to get, the grams of methanol, we actually have to multiply by a number bigger than 1 to actually get that liter that we want. Okay, so let's estimate this answer. Would everyone agree that 0.791 divided by 74? Well, actually, let's do it this way. Would everyone agree that 79.1 times 100 is 79, right? 79 divided by 74 for all practical purposes is 1. If you wanted to, you can make it 1.1, but it's 1. And 1 times 1,000 is 1,000. So our answer should be about 1,000 grams of methanol. So let's take a look here. 1.0 times 1,000 times 0.791 times 100 divided by 74, and we get 1,069 grams of methanol. How many significant figures are we allowed? Anyone want to voice it?
No, I think we're only allowed. Would we be allowed 4?
2.
2? 2. Oh, I didn't even see that one.
Okay, so how do we write this with 2 zig figs? And the answer is 1.1 times 10 to the 3rd grams of methanol. So that's the theoretical yield that you would need to actually get 1 liter. Okay? All right. Let's move on to the next one. So this next one we have a 2.634 gram sample containing impure copper 2 chloride dihydrate was heated. The sample mass after heating to drive off the water was 2.125 grams. What was the mass percent copper 2 chloride dihydrate in the original sample? So we're going to start with the question that is really asked here. What is the mass percent copper 2 chloride dihydrate in the original sample? So the answer to the question is a calculation. And the mass percent of copper 2 chloride dihydrate is going to equal the mass of copper 2 chloride dihydrate in the sample, this sample here, divided by the mass of the sample, times 100%. And this follows the formula of part over whole times 100%. This is the most general formula you can have for percent. Now, since we're talking about mass percent, we're talking about the mass of one thing over the mass of the other. And in this case, the sample is the whole, and the copper 2 chloride dihydrate is the part. So I think it's important to understand that this is the formula for percentage, and this is what it is specifically for this problem. So for this problem, you can see that we already have this. So we're halfway there. We just need the mass of copper 2 chloride dihydrate in the sample. And if we know that when we heat the sample up, it's going to turn into copper 2 chloride with no hydrate and 2H2O, we can figure out the mass of this stuff by hopefully one of these two products. Now, this weighs 2.6, well, I shouldn't say this weighs 2.364 grams. And I was going to write that down there, but it's not pure copper 2 chloride dihydrate. This is what we want, and we don't have it. So how do we get this? Well, to get this, we would need the moles of copper 2 chloride dihydrate. And to get this, we need the moles of copper 2 chloride, or we need the moles of H2O. Now, in our sample, so I'm going to write this down, there are actually two reactions happening. You've got copper 2 chloride dihydrate plus heat turning into copper 2 chloride plus 2H2O, plus you have some other stuff in there. When you heat it, it stays as other stuff. And these are the same. Now we know that if this weighs, say, X, and this weighs Y, we know that X plus Y is equal to 2.634 grams. So the nice thing about this stuff is when it's done, it still weighs Y grams. So that means that the mass difference is due to lost H2O. Okay, so that's important to know. Another way you could write this would be something like this. Copper 2 chloride dihydrate plus other turns into copper 2 chloride plus H2O plus other. This weighs 2.634 grams. And here, whatever this weighs, we'll call that Y, and Y, it's the same on each side. And here, this weighs, according to our problem, 2.125 grams. So here, if we, and I should say, this is not quite correct. I'm going to cross this off, and I'm going to write CuCl2 plus other plus H2O. And I'm going to say this weighs 2.125 grams. Because the H2O has been heated and it's left the test tube. So are you with me here? So here we can figure out that the mass of H2O is 2.634 grams minus 2.125 grams. And 4 minus 5 is 9. 2 minus 2 is 0. 6 minus 1 is 5. 2 minus 2 is 0. So we have 0.509 grams of H2O. And what we're going to do with this is we're going to take that and we're going to turn that into moles of H2O. And then we're going to turn this into moles of copper 2-chloride dihydrate. And then we'll turn it into grams of copper 2-chloride dihydrate. And then we'll finally be able to solve the problem. So here's what that looks like. Let's see, that's 18.02 grams. And then there's 1 mole of the copper 2-chloride dihydrate to 2 moles of H2O. So where do I get this ratio from? And the answer is I get it right from the formula. So this formula means that you have 1 copper 2-chloride and you've got 2 H2Os, or 1 mole to 1 mole to 2 moles. So that's where I get this from, the formula. And then I need the molar mass of copper 2-chloride dihydrate. Copper is 63.55. Chlorides are 35.45, and there's 2 of them. There are 2 H2Os, so I'm going to put 2 times 18.02. And when we get the molar mass of this stuff, we get roughly 63 plus 70, which is what, 133? 133 plus 36 puts it at about 170, I think. So let's check. And I get 170, so 170.49 grams of copper 2-chloride dihydrate per 1 mole of copper 2-chloride dihydrate. And here, I'm going to write this down here. We can estimate the answer here also. This is really close to 180, and 18 into 180 would go 10 times, so I'm going to go with that. 2 goes into 10 5 times, and half of 5 is 2.5. So I think the answer is going to be around 2.5, but because 18 doesn't go into 170 10 times really, it's less than 10, I think the answer will be a little less than 2.5. Okay, so let's see what we get here. 0.509 times 170.49 divided by 18.02 and also divided by 2. And sure enough, we get 2.41 grams of copper 2 chloride dihydrate. Now, after doing all of that work, it seems like we're done with the problem, but we're not. If we go back, we can see that the real problem is here. So we have to finish this. And to finish this, we're going to go ahead and use that formula where the mass percent copper 2 chloride dihydrate is equal to the mass of copper 2 chloride dihydrate. Now, hopefully, if you were doing this on a test, you wouldn't have to rewrite this because when you wrote it originally, you left yourself room to do the rest of the work. Over the mass of the sample times 100%. And here we just figured out that you have 2.41 grams of copper 2 chloride dihydrate. The original sample was 2.634. And then times 100%. And you can see that this number is going to be pretty close to 100% because this divided by this is almost 1. These differ by what? 0.23. And 0.23 is roughly 10% of this. So the answer should be around 90%. Now, why does this only have 3 zig figs? And the answer is because when we calculated it, the 0.509 grams only had 3 significant figures. Okay, so divided by 2.634, then times 100, and we get 91.4%. So there's your answer. Any questions on that? If you have any questions, raise your hand. Okay, then we're going to move on. We're just going to be like a machine and just keep going through these. And I'll be better about posting this one with the others. I don't know if you've noticed, but when I posted the Q&A this time, in the past when I post the videos, it seems like you can choose what video you want from the side. But this time, if you want to look at other videos, you have to go to the title and press that, and you can go to other videos. It's kind of weird. Okay, so this is another analysis of a mixture. At higher temps, sodium bicarbonate is converted quantitatively to sodium carbonate. And here you can see what happens is that when you heat this up, you remove CO2, you make the sodium carbonate, and you also make H2O. And then heating a 1.7184 gram sample of impure gives 0.196 grams of CO2. What was the mass percent in the original sample? So here, if we start this like we should start off with the mass percent sodium bicarbonate is equal to the mass of sodium bicarbonate in the sample divided by the mass of the sample times 100%. And what I'm going to do here, because I found this from the previous problem, is I'm going to do this, is equal to, and I'm going to put grams of sodium bicarbonate divided by, here's the mass of the sample, 1.7184 grams of sample. So I know that I'm working towards figuring this out here. the grams of sodium bicarbonate. So in this case, if we look at the reaction to sodium bicarbonate, without regard to the state, because that doesn't really matter to us, we get 0.196 grams of CO2. So we're going to turn this 0.196 grams of CO2 into moles of CO2, and that into moles of sodium bicarbonate, and that into grams of sodium bicarbonate. Because we're making the assumption that the only source of CO2 from this reaction is from sodium bicarbonate. Okay? All right, so let's take a look at this. We have all the information pretty much we need right here. So we're going to start with 0.196 grams of CO2. To go from grams to mole, we need the molar mass of CO2. And it turns out that 1 mole of CO2 is 44.01 grams of CO2. And for the moles of sodium bicarbonate, sodium is 22.98, or is it 99? Let me double check. 99. Hydrogen, according to our the periodic table that you get on the exam, is 1.01, so I'm going to use that. Carbon is 12.01, and oxygen is 16, so 3 of them is 48.00. And when we add these all together, 0.99 plus 0.01 becomes 0.01, carry the 1. And then here we have 48, 10, 11, 12, 13, 14, carry the 1. And then we have 3, 4, 7. So roughly 74. And when I look at these numbers and add them up together, I want to see if I kind of did this right. I know that 48 plus 12 is 60, 61. 61 plus 22 is what? 84, and I have 74 here, so I think I messed this up. 1, 2, 3, 4 plus 4 is 8, so it's 84.01. So even with this addition, you can estimate and see if you did it right. And clearly, I didn't do it right. So here, we're going to multiply first, though, by the balanced reaction, and I'm going to lower this paper so, oh, we have the balanced reaction right here. We're going to multiply by 1 CO2, 1 mole of CO2 per 2 mole of sodium bicarbonate. And then finally, we're going to multiply by this 84.01 grams of sodium bicarbonate to 1 mole of sodium bicarbonate. And here, since I have this written up here, I'm going to bring it on down. We can actually now calculate the mass percent with this number here. So let's see what we get. I'm going to estimate again. So how do I want to estimate all of this? Well, I think 44 goes into 84 2 times. I think 2 times 2 is 4. And the way I look at that number, I think at 20%. 20% of 4 is like 0.4. Or actually, 10% of 4 is 0.4, so 20% of 4 is 0.8. I think the answer is going to be 0.8 or thereabouts. And let's see what we get. 0.196 times 2 times 84.01 divided by 44.01 is equal to 0.748 grams of sodium bicarbonate. So that's not a bad ish. When I say 0.8, I got 0.74. So the mass percent sodium bicarbonate is going to be equal to that number, 0.748 grams over 1.7184 grams times 100%. And when you're estimating, you don't have to do anything really exactly. But can you see how 0.784 is less than half of that? So the percent yield should be less than half or less than 50%, but kind of close. So we expect the percent yield to be, in the range of like 40%-ish. And we get 43.5%. And, when you get an ish of 40% and you get a real answer of 43.5, you should be pleased with yourself. Any questions? Are you still with me? Okay. Then we'll just keep going. Okay, so for the next one, we have empirical and molecular formulas. So this shows you how to find the empirical molecular formula of something. And when you're burning a hydrocarbon, essentially the method is 1, take the grams of CO2 and figure out the moles of carbon. 2, take the grams of H2O and figure out the moles of hydrogen and go from there. Okay, so here we don't know what the formula is of this compound, so we can't write a balanced reaction. So again, we're going to take the grams of CO2 and we're going to get the moles of carbon. Because it turns out that when we do this, we take the grams of CO2, turn that into moles of CO2, and turn that into moles of carbon. This moles of carbon is how many moles of carbon are in the CO2. But in the reaction for this acetylene, you react it with O2 and you make CO2 and H2O. You can see that this oxygen has no carbon in it. So where does every carbon here come from? It comes from acetylene. Here, this oxygen has no hydrogen. So where does every atom of hydrogen come from? Acetylene. So that means the number of carbons here equals the number of carbons here. The number of hydrogens here equals the number of hydrogens here. And that can be used to get the ratio of atoms in the compound and the formula. So I like to always start with the CO2. So we have 0.379 grams of CO2 times 1 mole of CO2 per 44.01 grams of CO2 times 1 mole of carbon to 1 mole of CO2. A lot of students don't do this. They just go straight from here because you can see when we multiply by 1/1, the answer is going to be the same. Okay. Now, 1/10 of this is 0.44, and we have 0.37. So here, I think that the answer is going to be a little less than 1/10, maybe 0.09. Let's see what we get. 0.379 divided by 44.01, and we get I made a mistake. 1/10 of this is 4. 1/100th is 0.44. So we should get a little less than 0.100th. And we get 0.861 mole of carbon. So the second thing we do is we take the 0.1035 grams of H2O, multiply by 1 mole of H2O per 18.02 grams of H2O. And if you stop here, it turns out that the moles of H2O do not equal the moles of hydrogen. So we're going to do this. There's 2 moles of hydrogen for every 1 mole of H2O. It says there right in the formula. And when we estimate this, we get 2 divided by 18 is the same as 1/10. 10 will go into that 0.1 times, so around 0.1. So 0.1035 times 2 divided by 18.02. and we get 0.0115. Okay, now to get the formula, there's two ways to do it. One way is to take the bigger of these two and put it on top. And get a ratio. So I'm going to divide by 0.00861. And so we get 1.33 mole of hydrogen to 1 mole of carbon. Now we know that the formula cannot have a fraction for the number of hydrogen atoms. So this is also equal to 1.33 hydrogens per 1 carbon, because a mole ratio and an atom ratio is the same thing. So we know that we don't want to have a fraction, and 1.33 seems really far away from 1 to just round it. It doesn't seem fair. However, we can keep the same ratio, and I'm going to multiply the top by 3 and the bottom by 3. And the top we get 4 hydrogens, and the bottom we get 3 carbons. And so our formula ends up being carbon 3, hydrogen 4. If you're okay with that, let me know. Let me ask you this. What if you had gotten 1.25 hydrogen and 1 carbon? What would you multiply by?
And you do by 4.
Yeah. What if you got 1.66 hydrogen to 1 carbon? What would you multiply by?
Would you do by 6?
No, by 3.
No.
Check out in your calculator what 3 times 1.66 is.
4.98.
And isn't 4.98 pretty much 5?
Yeah.
Yeah.
I only said 6 because that gets you 9.96, which is 10. But
Yeah, but then you'll end up with here, it'll end up being 6 times this is what?
9.96.
Okay, so that would be 10, right?
Yeah,
And 6 times this is what?
6.
And would you write this down for the empirical formula?
No.
Yeah, empirical is the lowest ratio.
Oh, right.
Now, if
Yeah.
you got this and then made it into that, that would be fine.
Oh, okay.
I have seen some things be like this, 1.600 to 1. Okay? And here, the inclination is to multiply by 3, right?
Right.
But when your data is this precise, maybe you multiply by 10 over 10 and you get 16 hydrogens to 10 carbons, and it becomes C5H8. Are you with me?
Yep.
When the data is this precise.
Okay.
If you have 1.6 over 1, who knows? Multiplying by 3 might just be okay. Okay, so there's the empirical formula. Okay, this is another empirical formula one. We're going to skip this one actually. And we're going to go to this next one. Okay, so this is really an empirical formula and a molecular formula. Do you see how this one differs from the other one in that this one has oxygen? So the method for solving this one is 1, you get the moles of carbon. 2, you get the moles of hydrogen. 3, you get the grams of carbon. 4, you get the grams of hydrogen. And then 5, you get the grams of oxygen. And then 6, you get the moles of oxygen. And you can see that the first two things that you do are just like you did in the previous problem. The additional things are this. So let's do these first, and then we'll talk about why we do these things. So we're going to take our 0.3718 grams of CO2, multiply by 1 mole of CO2 per 44.01 grams of CO2, and times 1 mole of carbon per 1 mole of CO2. And you can see we get 4 significant figures here. And we get 0.008448 mole of carbon. I'm going to go ahead and kind of to the side here, I'm going to take that 0.008448 mole of carbon and multiply by 12.01 grams of carbon to 1 mole of carbon. And I'm going to get 0.1015 grams of carbon. And I'm going to take the 0.1522 grams of H2O times 1 mole of H2O per 18. I'm going to move this up a little bit. 0.02 grams of H2O times how many moles of hydrogen for 1 H2O? How many moles of hydrogen?
2.
Yep. And here, 0.1522 times 2 is 0.3. And 1.8 would be, if this on top were 1.8, not 0.3, but 1.8, we get what, 1/10. So that means if we had 0.18, we get 100th, and 0.3 should be more like 0.02 or something like that. So let's see what we get. Divided by 18.02, and we don't get 0.02, we get 0.01689 mole of hydrogen. And then down here, I'm going to say 0.01689 mole of hydrogen times 1.01. I'm going to put 0.08 grams of hydrogen per 1 mole of hydrogen. And the reason I use 1.008 here instead of 1.01 is because I have 4 zig figs here and I don't want this to limit it. So I get 0.01703 grams of hydrogen. Okay, so far we have this number here for the moles of carbon, this number here for the moles of hydrogen, and I would argue that this number is smaller and this number is larger, right? But we need the moles of oxygen. Well, we know that the compound weighs 0.1523 grams. And we know that this thing has 0.1015 grams of carbon. We know it has 0.01703 grams of hydrogen. Well, can we figure out how many grams of oxygen it has when we have these two masses and we know that the total mass is 1.523? And the answer is sure. It's the difference between this and these two numbers. So let's see what that is. And I get that the grams of oxygen is equal to 1.523 grams minus 0.1015 grams minus 0.01703 grams, which is, well, I had the answer here, but I erased it. Now, we don't really need to write this out here, but it is kind of nice having the grams of oxygen on one side and everything else on the other. Okay, so let's see what we get here. I get 1.404. Let's see, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. So it's good to hear grams of oxygen. Okay, so I think I did that right. I'm not sure. Seems like a lot of oxygen, I'll be honest with you. And what I'm doing here is I'm double checking everything. What I'm doing is I'm going back to this number here, 0.3718 grams of CO2. I know that that's got to be about 1/3 carbon. So that means about 0.12 grams of carbon. So that seems to be about right. I know that this has got to be about 1/100th of a mole of this. So 1/100th of a mole means that we've got to have about 2/100ths of a mole. So that looks good. And I'm just going to double check my answers here. Do you see why I got such a large number? Anyone want to point out my mistake?
Is it because you moved the decimal over for the total mass?
This is not 1.523,
It's 0.15.
0.1523. So 0.1523, and that's going to give us a completely different answer here. Okay, so 0.1523 minus 0.1015 minus 0.01703, and we get 0.0338 grams of oxygen. This is good to 4 places past the decimal. This is good to 4 places past the decimal. This is good to 5 places, so I'm going to round to 4 places past the decimal. Now, when you look at the masses of these atoms, 0.1, 0.017, 0.033, doesn't this seem to be more in line with what we expect than 1.4? So I think that's a better number. And so here, let me get out another piece of paper here and we'll write these numbers out. So we have 0.008448 mole of carbon, 0.01689 mole of hydrogen, and 0.0338 mole of oxygen. Okay, so what you want to do here is you want to pick which one of these numbers is the smallest. Do we agree that for these numbers, the one that seems to be the smallest, actually, and I've made another mistake. We have 0.0338 grams of oxygen, but we need moles of oxygen. So let's do that. So 0.0338 grams of oxygen times 1 mole of oxygen per 16.00 grams of oxygen. And here when I'm looking at this, I see that this says mole and this says gram, and that's why I realized I made a mistake. So divide this by 16, and we get 0.00211 mole of oxygen. Okay, so which of these numbers is the smallest? I would say that one's the smallest. Would you agree? 0.002? So what we're going to do here is we're going to do this 0.008448 mole of carbon to 0.00211 mole of oxygen. And I think you can see that this is going to end up being 4 mole of carbon to 1 mole of oxygen. We're going to do the same for hydrogen. We're going to do 0.01689 mole of hydrogen over 0.00211 mole of oxygen. And here, this looks like it's going to be 2 into 16. That's going to be 8 mole of hydrogen to 1 mole of oxygen. Okay, so I'm taking the other two and I'm dividing each of them by the smallest. And so we can see that the ratio is going to be carbon 4, hydrogen 8, oxygen 1. And I'm going to go ahead and plug this into my calculator and double check to make sure that it does come out to be 8. And it actually comes out to be 8.00. So it does turn out to be 8. And I'll double check this one. And this actually comes out to be 4.00. So this is the empirical formula. Okay, let's go back to the problem. It says if the molar mass is 72.1 grams per mole, what's the molecular formula? So molecular formula. To get that, you take the molar mass of the molecular formula divided by the molar mass of the empirical formula, and you get a multiplier. In this case, we have 72.1 grams per mole. And here the molar mass of this is going to be 12.01 grams times 4, which is 48.01 grams. 1.01 times 8, which is 8.08 grams. And 16.00 times 1, which is 16. And when we add these all up together, 8 plus 8 is 16, plus 6 is 2. Carry 2 because that's 20, and you get 72. So here the multiplier is 1. So we take this formula, and here's the multiplier, and it becomes C4H8O. And that's the molecular formula as well. Now, what if the multiplier had been 2? So clearly the multiplier is not 2, but let's say the multiplier had been 2. This is what the formula would end up being, C8H16O2. So do you understand what to do with the multiplier, Harry and Jackie?
Yeah, you should multiply it to the subscripts of the empirical formula.
Right. And to get the multiplier, you take the molecular formula divided by the empirical formula. That's all there is to it. And this number better come out to be a whole number. Okay, let's move on. So this is another empirical molecular formula problem, but it doesn't really do with combustion of a hydrocarbon. In the past, we've been dealing with hydrocarbons, which means they have hydrogen and carbon in them. And we also did a hydrocarbon with oxygen in it. So here we have a compound instead made of iron and carbon monoxide. This is actually called a coordination complex. So you burn this in pure oxygen to give you iron 2, or this is iron 3 oxide and carbon dioxide. So I'm going to write out the equation, and I'm not going to bother balancing it because that's not of interest to me. Just like when we did the hydrocarbons, we did not balance any reactions. Okay, so this is the reaction that's not balanced. Now, look at that iron in the products. Where does that iron have to come from? And the answer is, has to come from here. So if we can take this and calculate the moles of iron, then we get the moles of iron in this. Same thing here. Where does the carbon come from? Well, it has to come from here. So if we can calculate the moles of CO2, we can calculate the moles of FeXCOY and get the moles of CO. Or we could just do this. We could take the moles of CO2, get the moles of carbon, and then take the moles of carbon and get the moles of carbon monoxide. So let's take a look at this. We burn 1.5959 grams of this material, and we give 0.799 grams of iron 3 oxide and 2.20 grams of CO2. What is the empirical formula? So I'm going to take the 0.799 grams of iron 3 oxide, multiply by 1 mole of iron 3 oxide, and iron is 55.85, I think. Yep, and plus 48.
I think you accidentally stopped sharing.
Oh, my computer's trying to update.
Uh-oh.
Let's see if we can share again. Thanks for letting me know. I didn't notice. It's going to take a moment for my Elmo to, it shut off my elbow, so it's going to take a moment for the Elmo to reconnect. It's almost there. Okay. Okay, are we back?
Yep. Let's see you again.
Thanks for letting me know. Okay, so I get the molar mass of this stuff is 159.70 grams. And then there's 2 mole of iron per 1 mole of iron 3 oxide. Okay. So here I can see that the answer is going to be very, very small because of these two. This times this ends up being about 1.6. And 1.6 out of this is about 1/100th. So I expect the answer to be around 0.01. And sure enough, it's 0.01. Oh my goodness. 0.0006. Now I have 3 zig figs here, so this is good too right there. The second 0 after the 1. Zeros before the 1 don't count. Zeros after the 1 do count because we see the decimal. We have 2.200 grams of carbon dioxide, I believe. Yep. Times 1 mole of carbon dioxide per 44.01 grams of carbon dioxide times 1 mole of carbon to 1 mole of carbon dioxide, but also times 1 mole of CO to 1 mole of CO2. We could actually look up here and see that, well, you know what, for every one of these, we get one of those. That's going to be clear because there's 1 carbon here and 1 carbon here. But this is nice and clean. So here, to calculate the moles of CO, we're going to have 2.2 divided by 44. I know that 4.4 would be 1/10. So 2.2 is probably going to be about 0.05 or half of 1/10. And sure enough, it's 0.0500 mole of CO. So when we get the ratio, which one are we going to put on the bottom, the iron or the carbon monoxide? Which number is smaller, top or bottom?
Would the iron go on the bottom?
Yes, because it's smaller. Now, let's screw up on purpose, okay? Now we get 0.2 mole of iron to 1 mole of carbon monoxide. Clearly not the answer we want, correct? So
Right.
how would you fix something like this? And the answer is, well, realize you made a mistake and switch them, or you got to turn that into 1. How do you turn that into 1?
Multiply 5.
Multiply by 5, but if you multiply the top by 5, what do you have to do to the bottom?
Also multiplied by 5.
Yeah. Now, can you see how this is kind of a pain in the butt? Don't do this. Just make sure you put the smaller number on the bottom and the bigger number on top, and you'll be okay. And we get 5 mole of CO to 1 mole of iron, which means that the answer is going to be FeCO5. You guys okay with that?
Yep.
Okay. All right. Do you guys have time for another problem or two, or do you want to call it quits? If you have time, give me a thumbs up. If you want to call it quits, just give me a thumbs down. And don't worry, you won't hurt my feelings either way. Okay, Jackie's got time. How about you, Harry? Okay, so we're going to switch gears now. And we're going to do a solution problem. So just a very quick overview. A solution is homogeneous, and it's made out of a solvent and a solute. And the solvent is what you have more of, and the solute is what you have less. So if this is your solution, and these are dissolved particles, this is solute, and this stuff is the solvent. Now in aqueous solutions, the solvent is water. And we're focusing on solutions with water as the solvent. Okay, that being said, here you have some potassium dichromate dissolved in enough water to make exactly, I don't like this word, I think it should be precisely, because nothing can be measured exactly. Exactly means you know all the numbers. So if this were 500.00000 forever, that'd be exact. But you can never measure anything exactly. So precisely is good, because when you're precise to 500 point, that's different than being precise to 500.0. 500.0 is more precise. It's kind of like measuring things to the inches versus the yards. Inches is more precise. So if you measure the wheelbase of a bicycle and you find that the wheelbase is 36.2 inches, that's more precise than saying it's 3 feet. All right. So here, they want to know what the molar concentration of the solution is. Molar concentration. This is the same as molarity, molar, moles per liter. These all mean the same thing. And this is the one that's most useful because it tells us how to calculate it. So if we have a 0.123 molar HCl, that means we have a 0.123 molarity HCl, 0.123 molar HCl, and we even abbreviate it even more. Molar is an abbreviation of molarity. We abbreviate molar or molarity with a capital M. And this also means 0.123 moles of HCl per 1 liter of solution. And that is also the same as 0.123 mole of HCl per 1 liter of solution. So we even abbreviate solution. So these all mean the same thing. Okay? So how do you calculate the molar concentration? To calculate the molar concentration, you need 1, the moles of solute, 2, liters of solution, and then you divide. So normally you don't set this up as two separate problems and then 3 divide. You just do it all at once. So let me show you how we would do that all at once. Now, what number up here is going to help us get the moles of solute? I would say it's this one here. So I'm going to start with 2.335 grams. of K2Cr2O7. That's the molecule in question. It's not a molecule, it's actually an ionic compound. And then what's going to help me get the liters of solution? And I would argue it's this number here. So I need to turn that into moles, and I need to turn that into liters. I'm going to start down here because it's easier for me to do. Okay, so now I will have liters of solution on the bottom. And then here I need the molar mass of potassium dichromate, which means I have to do a little bit of calculating. So sodium is 39.10. So 2 times 39.10 plus chromium is 51 or 52.00. So that's just 104. I'm going to add 104. And then 7 oxygens would be 16 times 7, which would be 102, right? So times 1 mole of K2Cr2O7 for 284.2 grams of K2Cr2O7. So this is how you do the calculation. So let's see what the answer is going to be. That'll go into that 2 times. 2 times that is 5. 5 over 284 is going to be like 0.00 something, I think. It's going to be really small. 0.002. And I get 0.016. I got 1 0 too many in there, apparently. Four mole of K2Cr2O7. Actually, I need 5 significant, oh, this only has 3 significant figures. So I'm going to do my calculations again and make sure I got it right. Yep. Okay, any questions on this? Are we okay? If you're okay, give me a thumbs up. Oh, and I actually should put per 1 liter of solution, right? Because I still haven't gotten rid of that. So what's another way of writing this? Write this down another way. And now let me show you what I'm looking for. How do we know this is a solution just by looking at it? And the answer is because molarity is the concentration of a solution. That's how we know this is a solution. How do we know this is moles? Whoops. K2Cr2O7, my bad. How do we know it's moles of K2Cr2O7 per liter of solution? And the answer is that's the definition of molarity. You need to memorize it. Okay, what are the molar concentrations of the ions? So would you agree that if we have 1 mole of K2Cr2O7, that's equal to 2 mole of potassium and 1 mole of that? So do you follow me here? How do I know there's 2 of these? And it's because of this right here. And we know that this is an ionic compound. And this is a little bit confusing, but remember in our class, once you've identified the cation, the rest of it is the anion. And how do I know there's only one of them? And the answer is because there would be parentheses around this if there were more than one. And how do I know the charge is -2? Well, because all these charges have to add up to 0 for a neutral formula. Okay, so here's the ratios. So that means if I have 0.0164 mole of K2Cr2O7 per 1 liter of solution, we can multiply by 2 mole of potassium per 1 mole of K2Cr2O7, and we end up getting this number times 2. And I'm going to go ahead and abbreviate right away. So that's the molarity of the potassium solution. And if we wanted to do the chromate, or dichromate, my apologies, it would be the same work, and we get 0.164 molar dichromate. So any questions about that one? We good? Okay, I think we'll call it a day there, and we'll pick up with this on Monday. We'll do some more solution problems, and then we're going to get into some titration problems, and that's pretty much the end of the chapter. So we'll do some more solution problems, some titration problems on Monday, and we'll see you then. Over the rest of this weekend, you should expect me to be working on doing your grading. And I've graded 1 lab notebook assignment, and I'm going to be giving an announcement out to everybody. Some people did really good on their notebook. They have a lab notebook. They write in pen. They don't erase, things like that. And some people are not doing so well. So I want to make sure that starting with the quantitative analysis, that everyone is doing a really good job. For the older labs, since I haven't really given you much feedback, I'm going to grade them very leniently. If you take a look at the density lab notebook, you'll notice that you should notice that you got a 10 out of 10. But if you open up the rubric, you'll see what you would have gotten if I graded based on the rubric. So go ahead. Do you understand what I'm talking about there, you guys? Let me hear you.
You know, I understand.
Okay, so I'm grading the old labs very leniently, meaning you guys will probably get 8, 9s, or 10s. The very first one, I'm just giving everyone a 10, just to let you know. For the homeworks, I've given you how many answers have I given you? 3 of them, right? 3 solution sets, one for module 2, 3, and 4. And you can see what I'm writing on the homework, and that's an example of the stuff, the kind of work I expect to see. So those I'll probably not grade so leniently on because, except for the first one. After that, you should be shown all of your work. Any questions about that?
Nope.
And the kind of work I'm showing you is the kind of work I also expect on your exams. What kind of work do I expect on your quizzes?
None.
Yeah, I expect you to choose the right letter. And that's about it. Fair enough?
Yeah, that's
Yeah.
fair.
All right, thanks for your patience on the grading. I'm going to be, after I sign off, I'm going to go back to grading your exams. I wish they were more interesting. This is just boring work. All right, we'll see you Friday. You guys have a good
Great.
weekend, okay?
See ya. See you Monday.
Bye.
All right.
Bye.